Hello there, I'm Sajjad Rabi and welcome to this tutorial. In this tutorial, I will talk about three different methods of flip morphing, working with suction force, which is one of the simplest way of doing flip morphing, working with target force, which is a little more complicated, but the good thing about this method is it's useful for both PyroFX simulation and flip simulation. And at the end of the tutorial, I will talk about how we can create custom force in Houdini to control flip particles directly. And also we will see the difference between two different color model or color systems, RGB color model and RYB color model, or red, yellow and blue color model, which is useful in art. We will see how we can convert RGB color model to the RYB color model, and how RYB is giving us much more interesting result in terms of blending primary colors. So let's jump into the Houdini and begin it. Okay, as I said, one of the simpler way for doing flip morphing is using suction fluid or suction force. Very quickly, I want to show you how you can use suction force to do a simple liquid morphing. I'm going to create a simple sphere, push it up only along y-axis. I want to use flip fluid from object. Don't forget to select your object and click on the flip fluid object. The points are not so visible. Press D in the display options, geometry. You can increase point size to 10, and maybe we need to have dark background. Yes, that's better. We have very simple dynamic network for flip. We could have collision objects. I would like to use ground plane. Control click on the ground plane. That's good. Before adding suction fluid in our Autodesk network, we need to have target object. For doing that, I want to use font sub here, write something here, for example, JK. Suction force is working with the VDV volumes, so we need to have some thickness on this object. We could use poly extrude sub and set distance to 0.5, and also don't forget to turn on output back option. That's good. Let me increase the size a little bit. And I think we need to push it up because it's inside the ground plane. Yes, and transform here, translate Y, set it to 1.5. That's good. Now target, select suction fluid, select your target object, press enter, select flip object, enter again. As you see, suction fluid created two different nodes for us, anti-gravity and suction force. Suction force is responsible for computing the force for us, and anti-gravity is responsible for disabling this gravity on the points which are inside of the target object. Once they are inside, we want to keep them there, so we don't need to have any gravity for those points. In the suction force, if you go to the code tab, you can see Vex expression here, which is one of the best features of the suction force, because you can change the code based on your need. You can customize suction force based on your project and do whatever you like. We have same thing for anti-gravity here as well. And about how anti-gravity is working, it's just creating another force with the same amplitude or magnitude of the gravity force, but in the opposite direction. And that's why some of the parameters of the anti-gravity are linked to the gravity force here. About suction force, we have few parameters here. Volume sub, it's pointing to the target object. In the target object, we have new node here as well. It's just for converting your object to the VDB, as I said before. Oh, it's not so good. In the volume tab, you can decrease voxel size, for example, 0.025. In the Autodop network, we have inside distance, outside distance. The inside distance is just instance threshold for the points which are inside the target object, and outside distance, of course, is for the points which are outside of the target object. We have suction strength, its amplitude or magnitude of your force. Let's see what we have right now. Okay, some of the points are falling down. That's maybe because those points are far away from target object based on this distance, and of course maybe we don't have enough suction strength as well. So I'm going to increase outside distance and adding more suction strength. Yeah, that's better. We need to have more points. Let's try 0.03. Okay, now I want to do something more interesting for you. Instead of using static text here, I would like to use expression. Let's start with $F. Now we have frame number, but it's not good for suction force because the number is changing per each frame, and suction force doesn't have enough time to show that number to us. So we could change the expression to change the number only per each 25 frame. For example, we could have $F divided by 25, but don't forget to put it inside the backtick because it's expression and we need to have the result of the expression as output of the found inside the viewport. At frame 24 we have 0.9, and at frame 25 we have 1. Same thing for frame 49, 1.9, and then 2. But we want to just keep the first number, the very first number. For doing that, you could use the floor function. Here we go. At frame 24, we have 0, 25, it's 1, 49, and 50, and same for the rest of the frames. Go back to the Autodop network. It's good, but the number is not so visible because the fluid is so thick. To fix that, you have a couple of options. There is a simple trick here as well. You can decrease particle radius scale here to, for example, 1.1, but don't go below 1. And here you can play with inside and outside distance. Let's see what we have right now. Okay, that's better than before, but if you want to make it a little thinner, you can decrease the inside distance as well. Okay, that's good. I would like to take a flip book. And it was very simple method to morph your flip Floyd to the different numbers. Let's go to the other subject. We have another method to do flip morphing, which is using the target force. If you create dot network, we have a gas target force. Working with gas target force is a little harder than suction force because you need to have some other nodes as well. But the good thing about this node is it's working with both pyro simulation and flip simulation. So it's good to know about this node too. To add those nodes, the simpler way is using a tool inside the shelf. If you are working with Houdini 19, some of the shelf tools are not here by default. You need to add container tools and legacy PyroFX because the PyroFX which we have here is the sparse solver, but we need to have the regular Pyro solver for using this node. If I want to show you here, for example, if you create a smoke, the type is the Pyro solver sparse and the object is sparse as well. So I'm going to use the smoke here inside the legacy PyroFX. We need to have source, click on smoke. We have the regular Pyro solver, and then you need to have target object. In the container tools, select attract Floyd, press enter, select your container and press enter. You have three different options for attraction: volume, surface, or attract to the points. I'm going to use the volume one. As you see, the attract Floyd created some nodes here. Let me play and see what we have right now. Okay, if you are getting error on the target force, you could just copy this node here and use the second one. I think it's a bug. Now it's working. It's attracting toward the target object. And let me very quickly tell you what these nodes are doing. The first one is responsible for visualizing the target force in the viewport, this red volume. The second one is creating the gold field based on the density, because for target force we need to have gold field. And here we are reading density information from the target source. If you go to the target source, we have some new nodes here as well. The torus converted to the points. We are creating density and temperature attribute, but the temperature is not useful for target force. Adding some noise, and finally convert those nodes to volume. We are reading density from target object and copy density to the goal field which we created here. And in the target force, we are reading density, goal, and computing the target force. We have a couple of options to control target force here. If you wanted to use target force with sparse solver, not regular Pyro solver, you just need to copy and paste these red nodes in your sparse solver network. But honestly, you need just to copy these nodes. And this part is not necessary. It's just about reading the gold field and density and blur the gold field based on these parameters, but it's not required for Philip or sparse solver. You can keep it, but it's not necessary. So I'm just going to copy these nodes, and now you can remove Autodop network, Pyro, and this one is target. Yeah, let me rename it to target. Okay, now inside the PyroFX, control click on the smoke. We have sparse smoke. Paste those nodes here and connect it to the advection or second input of the Pyro solver. Okay, we need to rename it here as well. It was target, yeah. Now we have target force for Pyro sparse solver. Right now, entire smoke is advecting toward the target. I'm going to do something here. Set this point to 0, the value of this point to the 0. Now, only a small portion of the smoke is advecting toward the target force. You can control it by minimum and maximum distance. Okay, now what about flip simulation? Again, we need to keep these red nodes. Control C. I'm gonna create sphere in the particle flows. Again, Philip Floyd from object. Instead of increasing the size of the points inside the viewport, you can use guides in the Philip Floyd object, particles, visualization to spheres. You can control the scale very simply here. Okay, now paste those nodes here. You must connect the output to the volume velocity input of the flip solver because target force is manipulating the volume velocity, not particle velocity. And if you play, you would have a couple of errors because for flip simulation, you need to do some more extra works to make it work. In the first stage, inside the target, you must have VDB version of the torus, not the regular 5 VDB. So you can use the VDB from polygons, fill interior, and I guess that's it. Inside the Autodop network, in the match target, we have surface instead of density. Density is useful for pyro simulation. In flip simulation, we don't have density field at all. If you wanted to visualize surface field in the viewport, you can select your Philip Floyd object, visualization, turn on surface, go to the second frame, and here is your surface field. So we are creating goal based on surface, and here we are copy goal to the surface. Sorry, here we are reading surface from target force, from target object, and copy it to the goal field which we created here. And don't forget to change density here to surface as well. In the target force, in the fields, we don't have density, we have surface, and I guess that's it. Oh, and don't forget to turn on liquid mode because we have Philip solver. I think target object is so far away, and the target force for Philip is only working when it is close enough to your target object. Great, yeah. And you can play with these parameters, of course. If some portion of your flip is falling down. And that's it. If you wanted to improve the jiggly motion of your flip points, you can very simply use the pop drag force and connect it to the second input or particle velocity of the flip solver, because of course pop drag is only working with the particles. The good thing about the flip solver is you can manipulate particle velocity and volume velocity separately. Nice. Maybe we need to have more particles. Okay, now let's see how we can create this project with target force. I'm going to use the same setup which we make just now. Inside the target object, we need to have another geometry as numbers. So again, I'm going to use font. Same expression as before, $F, $F divide by 40, because I want to change the number per each 40 frames. And Control Enter. Okay. Set the font size to 4. It should be toward y-axis. So I'm going to drop down transform sub minus 90 degree around x-axis. And of course we need to have poly extrude as well. Poly extrude. Set distance to 0.5, turn on output back, convert it to VDB, decrease voxel size. Yeah, that should be enough. And let's check the simulation. I would like to change the particles inside the viewport from sphere to points. Turn it back to particles. Okay, it's working. We need to have ground plane, control click, and put the target object down. Let's turn it back to 0, 0, and 0. Hide ground plane in the viewport. Let's increase the number of particles as 0.025 or maybe 3 could be enough. And do a simple flip book. But before doing that, let's change some of the parameters of the target force. Right now, we have very intense target force for entire fully particles, but I would like to have some remaining particles when the number is changing to different one. So let me decrease the force scale 25, minus 2 for a minimum distance and 5 for maximum. Add a point here, put it down. Yeah, as you see, some of the points has less target force. Here is the flipbook working very well. If you want to have more particles around the number, you can use viscosity. Not too much, but just a little bit. So in the flip solver, volume motion, viscosity, you need to turn this option on and turn viscosity by attribute on. The rest should be fine. And don't forget to select your flip object in the initial data. Don't forget to add viscosity attribute option. But also this one the simpler way could be using this button here, make viscosity. It's turning on all of these options automatically for you. Now we should have viscosity. As you see, some particles are sticking to the ground plane, but the thing is, most of them are completely stopped on the ground plane. I want to have a little motion on those area. For doing that, you can turn on slip-on collision. By default, all of the viscous particles are sticking to the ground plane or any collision object. But with this option, we could let them slide on the ground plane or collision object. So I am gonna turn this option on and set the slip scale to 0.2. As you see, they are sliding on the ground plane. Let's do another flipbook and see what we have right now. You can see these remaining particles in my render as well. For example, this part, and you are sliding on the ground. Okay, I think the simulation part at this stage is good. Now let's go to the next part and see how we can add these colors to your flip simulation. To apply color to the particles, you can simply use pop color dot. The blue color you are watching in the viewport is coming from visualization part of the flip fluid object. If you go to the guide and set this parameter to none, you don't have any blue color. And here, let's say I would like to have red particles. But this color is the same for entire simulation. I would like to have different color on every 40 frame based on noise pattern. For doing that, I've used Subsolver in my project. Subsolver is a great tool in the dynamic network. If you go inside it, you have geometry network, so you have access to all of the subnodes here. You are reading information from dynamic network. At this point, you can manipulate or edit those information by any subnode and then send it back to your simulation. In this case, let's say I would like to change the color of the points. I'm going to use the color sub, the regular color sub. Let's turn it off for now. And I want to change the color per each 40 frame. Set it to random from attribute. By changing the seed, you will have different color. But I want to do something to change the seed only on every 40 frame. For doing that, we need to use same expression as what we had before here. So on every 40 frame, we have different color, but it's not what we want. We want to have some noise pattern as well. We need to change the color only on those noisy pattern area. You need to go to the target object. Here, I'm going to use the actual geometry of the number. Later on, I want to apply a noise pattern to the points, but right now we don't have any points on the surface. It's just completely flat. There is just one primitive. To fix that problem, you can use remesh sub. If you need to have more points, you can decrease target size here. Let's say 0.1, then point swap. Let's call it noise. Drop down anti-alias noise. Position to P, result to the CD. But the output of the anti-alias noise is not between 0 and 1. So you need to clamp it to 0 and 1. The parameters maybe 10 amplitude and increase frequency to 3, 3, and 3. That's good. The pattern is almost same for all of the numbers because we are not changing the offset. So promote offset by middle click, and here again I'm using this expression. We have different number per each 40 frame. Maybe it's better to multiply it by some big number, maybe 30. Okay, now we have different noise on every 40 frame. In the next part, I need to remove black points with simple and blast node. Based on CD attribute, the red value of the CD, if the red value is less than 0.1, just remove that point. And don't forget to set group type to the points because CD attribute is stored on the points. And as you see, we have some unuseful points. They don't have any polygons. To remove those points, you can simply use the add sub. In the polygons, turn on remove unused points. And let's call it CD mask. Inside the Autodapp network subsolver, you can grab that object here with object merge. CD mask. Connect color to this object, and now at this part we have flip particles, and here we have the object which is coming from the target network. Okay, now I want to transfer color from this part to the flip particles. So we need to use the transfer attribute. First input, second input. We just want to transfer CD point attribute. Right now, the distance threshold is too much. Let's say we need to have 0.5. If you want to have smoother or softer edge, you can increase blend width a little bit. That's good, but we want to transfer color from this part to the flip particles only on every 40 frame, not for entire frame range. So for doing that, you can use switch, first input, second input. Okay, if select input is 0, it means that we are reading actual flip particles, but if it's 1, we are updating the color of the flip particles. So let's write some simple expression here. $f percentage 40. On every 40 frame, we have 0. Let's say, for example, at frame 39, it's 39, but at frame 40, it's 0. At frame 79, it's 39 again, and at frame 80, it's 0. But we want to have 1 per each frame. So for doing that, you can use, for example, condition statement. If the result of this expression is equal to 0, it's 1. Let's test it. At frame 39, it's 0. At frame 40, it's 1. And again, 79, it's 0. 80, it's 1. Let's check the simulation. The color of the points are white because at the beginning, we are not updating the color of the points. We could use pop color here to apply some default color only at the beginning of the simulation. We don't want to use pop color for entire frame range because after first frame of the simulation, we are updating the color of the particles with this part, not with pop color. For doing that, you can play with the activation option here. If it's 1, it means that we are using this node in the simulation. If it's 0, we are disabling the pop color. So let's say the start frame is 1, copy parameter, paste relative reference, and if frame number is equal to start frame, the current frame is equal to start frame, it is 1. But at the beginning of the simulation, we are not computing this part of the dynamic network. It's happening on the next frame after first frame, which in this case is frame 2. So just add 1 to start frame. Like that. Now we have default color, which is red. And after frame 39, we should have okay, there is a problem. Let's go inside Subsolver. Okay. Oh, I forgot to use double equal sign here. Working very well, but we don't have any color blending. For example, the red points here are staying red even when the neighbor points are pink. But in this project, we should have some kind of the color blending as well. For doing that, you can simply use attribute blur sub inside Subsolver. So drop down attribute blur. We want to blur CD attribute. And let's say 2 as a blurring iteration. And don't forget to set influence type to proximity, because right now we don't have any polygons or edge between each point. In this case, you need to use proximity. The first one is useful when you have polygons and edge and something like that. And let me do a quick flipbook. The flipbook is done, and here is the result. It's very good, and it is exactly what we wanted. We have blending color as well. But the problem right now is we don't have any control over the color per each number. It's just using the random function as a color. If you want to have more control over the color, for example, you want to have red when the number is 2, or you want to have green when the number is 3, you can use point swap. Let's call it color picker. Inside it, drop down switch node, promote switcher, middle click, and let's call it color index. Okay, input 1, promote this parameter. The type should be color, and let's promote the first 10 input. What switch node is doing is just selecting one of these inputs as an output or result based on switcher number. For example, if switcher number is 0, we are using input 1. If it's 1, if it's, for example, let's say 5, we are using input number 6 because it's starting from 0, not starting from 1. And of course, if it's 9, it means that we are reading input 10 as a result. Don't forget to select all of these inputs and set the type to color, and we have different color inputs here. Let's define some color, for example, red for the first one, green, blue, yellow, something like that. And if color index is 0, it's using red, 1, 2, 5, and 9 for 10. Now we are using that expression here again, floor $F divided by 4. So at frame 39, it's 0, we are using red. At frame 40, it's 1, we are using the next color. And at frame 80, we have blue, and same for the rest. So I'm gonna use this node instead of color. And I would suggest you to use output node here because sometimes you might forget to set display flag to the last node of your network. For example, let's say display flag is at this point. On that case, subsolver is computing your network from this point, not from the end of your network. But if you are using output node, you guarantee that subsolver is computing your entire network from endpoint. Let's do another flipbook. Okay, so far so good. I think that's good, and we could go to the next part. Now it's time to cache out our simulation to the disk. Before doing that, I would like to increase number of flip points. Let's try 0.01. Inside Flip Mesh, we have Fluid Compress node. Don't forget to add CD attribute here because we already generated CD attribute in the dynamic network. If we want to keep this attribute after Fluid Compress, we should make sure that we have CD here. I already saved my simulation to the disk. Just let me load it. And if you wanted to check the particle of your flip, you can use surface preview here. We have particle fluid surface, the polygon version of your flip. If you check it frame by frame, you should see that we have some flickering issues. Usually to fix those flickers, using spherical method is giving you better result rather than using average position. So I'm going to use a spherical, and it's better to have some smooth as well. If you check it, yes, we have less flickers. Okay, that's good. Now it's time to start to work on lighting, shading, and rendering. For the rendering part, I would like to use Solaris and render my project with Karma. Just let me organize these nodes in the object level. We have flip mesh. We have ground. The ground plane we have here is useful for dynamic. I can use this as well, but I prefer to use another one. Okay. And let's change the interface to Solaris. We could use stage network here, and also we could use lab network here as well. I'm going to use scene import to import all of the objects inside the Solaris network, and of course you can use sub import as well. I prefer to use this method. I want to make everything so simple in this tutorial. You can import all of your object nodes from this network inside Solaris with just this single node. In the object, I'm going to choose flip mesh and of course grunt. Now we have both of them here. And don't forget to turn this option off, because the flip setup already created a shader for us, the basic liquid shader, and it's assigned to flip mesh if you check it here. But I would like to create my own shaders inside the Solaris. So if you check UST graph here, we have basic liquid which is coming from the regular material network. But if I turn off this option, I don't have that shader here anymore. We need to have camera, control click on the camera, like the viewport, maybe this camera angle. We need to have environment light, control click. We need to have spotlight, change the direction of spotlight somewhere here. And if you want to see rendered version of your project, you can change the perspective to Karma. So far so good. For the skylight, environment light or dome light, you can use HDRI texture here. I'm going to use the one which is installed with Houdini. In the HDRI directory, I'm going to use this one. And spotlight seems good. We have some nice shadow here. Yeah, for now let's keep it as it is. Okay, what about shader? To create our shaders, we need to use material library node. Inside it, I'm going to use principal shader, one for flip simulation, let's call it liquid, and another one for grunt. To assign those shaders to corresponding object, you can use material assign or assign material. Control click on this button here. For the ground, I want to use ground shader. Add another one. Control click. For the flip mesh, I would like to use liquid. Now inside material library, and also if you check these three here, we have our materials here and the shaders, sorry, and the objects. Okay, for the ground, I want to assign grid texture. In the textures tab, turn this option on, and we have grid texture here, grid.rat. Press accept. Now we have grid. I think specular of the ground is a little harsh. Let me decrease it a little bit. In the reflectivity, set it to 0.5, 0.25. A little more roughness would be nice. Okay, that's good. Let's turn off the light icon inside the render view by using this button. Okay. Okay, by default, Principled Shader should use the color attribute from Flip Mesh as a base color, but right now it's just using the base color and it's completely gray. I think that's because inside Flip Mesh I forgot to add CD in the particle fluid surface as well. So if you want to keep CD attribute on your mesh, you need to add CD here too. Okay, now it's working. But I would like to make it transparent. In transparency, set transparency to 1. We have use point color here too, but instead of using this option, I prefer to import CD attribute by using bind node, because in that case I can do some customization on the CD attribute before sending it to the shader. So let's do that. But the thing is, by default, if you are, for example, working with Mantra, what you need to do is just reading CD attribute by bind node and connect it to the base color like that. But it's not working like that in the Solaris. Let's change the type to vector. Because if you check Houdini help, it's mentioning that some of the attributes are converting to the different attribute when you're working with the Solaris. For example, P is going to be points, or N is normals, and for the CD it's going to be display color. So we need to use display color instead of CD. Let's do that. Because it's completely transparent, the base color is not visible. Let me make it opaque. Okay, now we are reading CD attribute by this node, and with this method we can do something on the CD attribute before sending it to the shader. For example, I can use color correction node. Maybe less saturation, something like that. Okay, for transparency, we need 1, and I need to connect the output of this node to the transmission color as well. Now we have some color in our liquid. some parts are completely black because the shadow in those area is black. To fix that problem, we have two different methods. We can use castix inside the geometry and shading of the karma node. Just turn this option on. Or we have option here inside the material as well. If you go to the opacity, we have fake castix. I believe this method is a little faster than working with the castix parameter inside the karma. So I'm going to use this one. Now everything is good. Let me play more with the shader. I'm going to change the distance of the transmission. Set it to 0.3. That's much better, but the remaining liquid on the floor is not looking very well. Let me take another snapshot here. You can see your snapshot by clicking on this button here, like that. Yeah, as you see, the liquid is so unrealistic in this area. And we have some weird specular as well. If you check my render, we have much better look of liquid on this area. Okay, what I did was flattening the flip mesh on this area. So let's do that. Go to the object network flip mesh. I'm going to import ground object. That's good. And we have flip mesh, point warp. Let's call it flatten. Second input to the ground. To flatten the mesh on this area, we could use XYZ distance. So I'm going to drop down XYZ distance node, position to the position of the flip mesh, input a second input of the point warp, which is ground. And it's giving us some information of nearest primitive of the ground to the current point. If we want to extract some attribute from the second input, we could use primitive attribute node. Prim to prim, UV to prim UV. I would like to read P attribute and of course connect phi to the second input, which is ground. Okay, right now if you connect the output of prim UV to the P, you can see the entire flip mesh is flattened on the ground, but I want to do flatten only on this area because the remaining liquid on the floor is so thick on this area, and we don't want to touch anything on this area. So for doing that, we can use the distance of the XYZ distance. So if the distance of the current point, let's suppose we are talking about this point, if the distance is more than certain amount, we don't want to do anything on this point. But if the distance is less than certain amount, we want to do flatten on that point. For doing that, we can use the fit range to change the range of the distance, connect the output of the fit to the CD just for visualization purpose. Okay. For now, let me disconnect this line. You can control the range by source max. If you want to have more control over the distance, you can use ramp attribute. And of course, the type should be float.
To have more smoother result, set interpolation to B-spline. That seems good. Now we want to do flatten only on the white area. So we must use the output of the RAM for flatten operation. And also the flatten should be happening only toward y-axis. We don't care about z or x-axis of the point. So I'm going to use vector to float and float to vector, x to x, z to z, another vector to float for prim UV, okay. I'm going to use mix swap. The first input should be the original y position of the points. The second input is the new flattened position of the points, which is this node. And you can connect the output of the RAM to the bias. And the output should be here. Okay, it's working. Let me disconnect this line. Now we have flattened liquid only on this area, not entire flip mesh. Let's go back to Solaris network. I think we have some intersection with the ground as well. It's making some artifact in rendering. To fix that problem, we can push the ground plane up a little bit at this point. So I'm going to use transform sub and use a small number here, 0.01 for example. If you check side view, we have some offset. Now go back to Solaris network. The result is a little better, and also we need to do something inside the shader as well. What I did in this project was, beside of the flatten, I was using opacity as well. For this area, we don't need to have full opacity. So we must control the opacity inside the shader for this area. Right now, we don't have any attribute to control opacity. So let's come back to the flip mesh. We could use the output of the RAM to control opacity. If you check the output, it's something like that, right? So, connect these to P. I'm going to use bind export to create my custom attribute. The name is edge mask. Inside the shader, you can import that attribute with bind. Because it's custom attribute, there is no need to rename it to something else, same as what we did here for the CD. No need for that. Connect the output to opacity scale, but the result is opposite. We need to invert the edge mask. For doing that, you can use the complement node. Okay, that's what we want. Do another snapshot, double click. Okay, that's good. But if you go to the flip mesh, we are using same ramp for both flatten operation as well as controlling opacity, which is not good, because if you, for example, if you are happy about the flatten and you're not happy about the opacity, if you change the ramp, you are going to change both of them. To fix that problem, you can use another ramp separately for opacity. So here you can remove edge mask at this point, copy this node, and we are not going to change the position of the points because we did that already with this node. We need just to have, oh sorry, XYZ distance. And just for visualization, let's connect it to the CD. Yeah, now we have two different ramp. I can control this ramp only for opacity. Let's call it edge mask. And don't forget to create edge mask. Maybe it's so transparent. Go back here. You can visualize edge mask with this method as well. Open this window and click on edge mask. It's creating visualizer automatically for you inside the viewport. Let's play with fit here. Okay. Check the render again. Oh, that was too much. There is a problem. I think it's coming from XYZ distance because, for example, on this part we have some kind of the line. Let's check it. Maybe that's because we are changing the actual position of the points here, and at this point we are reading that flattened version of the points as an input of the XYZ distance. Instead of that, I'm going to connect it to the actual flip mesh, if it makes sense. Yes, we have different results. So let's do that separately. Here is the flattened version. Here we are creating edge mask. I'm going to use attribute create attribute copy and copy only edge mask from this side to the other side. Now let's play with the ramp. Yeah, it's better. So far, so good. We could have some more sharper specular and maybe a little more saturation on the in the color inside the Solaris material library. Increase saturation here and maybe a little darker. For specular, we could decrease reflectivity because the roughness in the specular here is affecting the transparency as well, the refraction I mean. And instead of that, we can use the coat and we have separate roughness for the coat. To have very sharp coat, we could use a small number like 0.5. And also, it's good to use normal sub at this point as well to make sure the normal direction are good, because we did some change in the position of the points here and we need to update the direction of the points normal based on the new position. Right now we are using just one single shader for flip, which is liquid. But if you check my project, I have three different shader. At the beginning, I have liquid shader. At this number, I'm using metal shader. And later on, for example, at number 8, I have plastic shader with subsurface scattering. So how we can do that? Let's say we have three different shader, metal, liquid, and plastic. We can have just one single principal shader, and by changing some of its parameters, we can turn it to metal, liquid, or plastic. But also there is another way. We can have three different principal shader per each one, and then by using mix swap we can decide which shader we want to use. In this tutorial I'm going to show you both of the methods. Actually, I'm going to use one single principal shader for both liquid and plastic and another one for metal. I think using different principal shader per each one will be much more simpler to implement, because if you want to use just one single principal shader for three different material, it will be so complicated to implement. You need to take care of many parameters of that principal shader. But as I said, let's do both methods in this tutorial. Before doing anything in the material library, we need to prepare two more point attribute from simulation. The first one is SSS attribute to drive plastic shader, and the other one will be metal attribute to drive metal shader. So let's do that. Inside dynamic network, inside the subsolver, in the subsolver we have color picker. I'm going to use this node to create metal and SSS attribute as well. So here is another one. Let's call it SSS picker, and the type of those attribute is float. So inside it, select all of these inputs and change the type to float. Let's call switcher to SSS index, and we need to create that attribute here, bind export. Let's call it SSS, and make a copy of this node. It's for metal. Metal index. The name of attribute is metal, and I think that's it. Okay, be careful about these numbers because, as I said, the switcher is starting from number 0. So number 0 means input 1. So if we have 0, it means that we are using number 1. But what actually we are seeing in the viewport in the Philips simulation is number 1. So number 1 is 1, is number 0 is 1, number 1 is 2. To fix that problem, we can subtract this expression by 1. And same for metal picker or metal selector, maybe. And same for color picker. Okay, so with this expression, input number 1 will be number 1 in the viewport as well. I want to use plastic shader only for number 2. For the metal shader, I'm going to use metal shader only for number 3 and 4. 0 means a regular liquid shader, 1 means plastic shader, and here for the metal, 1 means metal shader and 0 means either plastic or liquid shader. Okay, connect it here and add those attributes name here. In the flip mesh, don't forget to add those attributes, SSS and metal. Then save it to the disk. The simulation is done. Let's test it to make sure those attributes are working correctly. At this point, we have SSS and metal. Okay, just drop down attribute wrangle, temporary, color equal SSS. So number 0 is liquid, number 1 is liquid 2, but number 2 will be plastic. For the metal, number 3 and 4 will be metal. So it's working. And here we also need to add SSS and metal. Let's go to the shader. First, let's start with plastic shader. I'm going to import SSS. Yeah, the brighter is better. Okay, uh, one means plastic, right? So we need to connect it to SSS. We are using subsurface scattering, but once it is plastic, we don't need transparency anymore. So I'm going to invert SSS and then use it to control transparency. Now we have subsurface scattering, and also we need to connect the color of the points to SSS color as well. In the subsurface scattering section with Karma, usually we're getting good result with random walk. Now let's go for metal shader, another principal shader. And let's assign it to this object temporary. Turn off point color and make it a little darker. Set metallic to 1. Okay, that's good. Call it metal. Now we need mix layer mix, not mix. The first input will be this shader. The second one will be metal. And to control the alpha, we need to use metal attribute. And here is, for example, flip shader. Okay, at the beginning, we have regular transparent liquid shader. And for number 2, we have subsurface scattering shader, which is deriving by this attribute. And for number 3 and 4, we have metal shader, which is deriving by this attribute. And also we might need to connect edge mask to opacity input of metal as well for this area. Okay, so far so good. I think that's what we wanted. I'm going to do some snapshot and show you the result. Okay, it's done.
For example, for frame 1 we have liquid, for frame 2 we have plastic, frame 3 it's metal again, and for number 5 it's going to be liquid again. Just one thing I should mention that is, if you remember, to test this shader I drag this shader in the render view to assign it to my flip mesh, and with this method Solaris is creating a new assigned material at this point, but I want to do this with my own assigned material. So just remove this one, and here for flip mesh we need to select flip shader. That's it. To render your project to the disk, you need to drop down Karma node and point it somewhere in your disk. The camera is correct. For the resolution, we can, for example, use 1920 by 1080. And here we could increase pixel samples. If you check our flipbook, specifically for subsurface scattering, we need to have more samples. It's too noisy. So here, if you change convergence mode to distributed, we can increase samples specifically for subsurface scattering. For example, I can increase it maybe 16, and we don't have any volume. We could decrease reflection samples and refraction a little bit just to make our render faster, but for final render you can use more numbers here, and same for diffuse, maybe 2 for test. Okay, and then press render to disk. The render is done. When I was checking it, I noticed that we have some problem here. For example, here when it's turning to plastic shader, we have some visible noise on this area, and also when the color or shader is changing to the different one, it's affecting the remaining liquid on the floor as well. If you check this frame, for example, this part is going to be green on the next frame, which is not good, and same for this part. So I made a couple of changes in my setup to fix those problems. The first one is inside the Autotop network for the floor, changing color on the floor. What I did was just grouping the points above the ground by using group expression. If the position of the points is more than 0.1, we are putting it inside the top group, and then inside the attribute transfer, we are transferring color and SSS and metal attributes only to those points, not all of them. So it's not affecting the remaining particles on the floor. And also to fix the problem on this area, to make it more smoother, what I did was inside the flip mesh network, I've used attribute blur to blur subsurface scattering and metal attribute, putting 3 as a blurring iteration, and that's it. And here is the render of the project with those changes. As you see, we have better result, and it's pretty much close to what I did before. Of course, I did some pre-com in this version inside Nuke software.
the setup for this project is almost same as what I did during this tutorial. Of course, I put the project of this one at the description below as well. It's good for you to take a look at to both of the project and see what's the difference between these two projects. It's mostly about just the parameters, the different pattern of the noise, a little bit maybe difference inside the shader and the lighting source. But the most important thing is for this version, I was using Mantra. So it's good for you to see how you can rebuild everything with Mantra engine as well. And if you wanted to keep going with the Karma, you can keep going with this project which I built for this tutorial. And there is still a small problem at the beginning. As you see, the liquid is completely black. That's because at the beginning we don't have any color attribute or CD attribute. If you go inside the Flip Mesh network at the beginning, here we don't have any CD attribute. And if you go to the next frame, we have CD attribute. Probably we did something wrong here when using the pop color, but it's not so important because very simply you can add CD attribute just for the first frame, for example, by using a regular color sub and a switch node. For example, red color or white color based on the color of the simulation at the beginning, which is red in this case. And okay, that's it for now. Let's go for the other subject of this project. If you check this project more closely, at the beginning we have yellow color, and then we are injecting the blue color to the flip simulation, and the blending result between blue and yellow is green. But it's not like that when you are working usually when you are working with any 3D software, because in most of the 3D softwares we are using RGB color system or color model. What we need here is using RYB or red, yellow, blue color model or color systems. So you need to convert your RGB color system to the RYB. And if I want to show you the difference between these two color systems, and in the left side we have RGB and the right side we have RYB. There is two different between these two color models. The first one is about the primary colors. Here the primary colors are red, blue, and green. And the secondary colors are magenta, cyan, and yellow. And in the right side, the primary colors are red, blue, and yellow. So here, yellow is one of the primary colors, but here the green is one of the primary color. And here the secondary colors are purple, green, and orange. The other difference between these two color systems is here the color model is additive, which means that if you want to create other secondary colors, you need to add primary colors. For example, for magenta, we need to add red color to blue color. Or for the cyan, we need to add blue and green color. But here, the color model is subtractive, which means to have, for example, purple, we need to subtract red and blue. And for the green, we need to subtract blue and yellow. And same for the orange. And also, as you see, the subtraction of all of the primary colors is black, but here the addition of the primary colors is white. If you search around the internet, you will find lots of free source code with different programming language to convert RGB color to the RYB, or in the opposite way. What I did was choosing one of those source code and translate it to the VEX code, so I can use that VEX code in my project. I already put that VEX code inside the digital asset, and if you download the project of this tutorial, you will have access to that digital asset as well, and feel free to use it in your own projects. To install that digital asset in your project, you need to go to the assets, install asset library, and then install ryb underscore rgb.hda. After that, you will have two new nodes in the WAP network. If you drop down point WAP, under JK, you will have RGB to RYB, and of course, RYB to RGB. And if you wanted to see how I've built this digital asset, you can just dive inside it and you will have full access to the VEX code of digital asset if you wanted to know how this operation is working. To test this project, I've built a very simple RGB color wheel, and here is RGB color wheel, the one we are seeing in the viewport. And after that, I converted the RGB to RYB color model, and here is the result of RYB color wheel. You can check that here as well. At the left side, we have RGB color wheel. The primary colors are red, blue, and green, and the blending result of blue and green will be cyan, same as what we have here, red, blue, and green, and here is the cyan. In the right side, we have RYB color wheel. The primary colors, of course, are red, blue, and yellow. The blending result of the blue and yellow will be green, same as here. Red, blue, and yellow, and here is the green. And of course, you can turn it back to RGB color system by using another node, RYB to RGB, for example, and inside it, instead of this node, you can use RYB to RGB. And the result will be exactly same as what we have at this point. Let's come back to the project again. Here is the project of this version. I've used RGB to RYB node here after reading the simulation file from the disk. We have blue color, we have yellow color, and of course we have green color. Just be careful, because if you check the colors before this node, we have green color and blue color. The green color you are watching inside the viewport is not the actual color, because as I said, Houdini is using RGB color system in both viewport and even the UI. If you go inside Autodesk network, inside subsolver, here we have green color. The value is 0, 1, and 0. But we are going to use RYB color system later on. So the primary color will be red, yellow, and blue, not red, green, and blue. So the one here is referring to the yellow color, not green color. So the green color here will be yellow. Okay, that's the end of the first part of this tutorial. In the next video, I will talk about this project
and I will show you how you can create custom force to control fluid particles directly. Thanks for watching this video and see you in the next tutorial.